Tonight, a black hole swallows a star, and with it, every secret that star ever held. Quantum physics swears information can never be destroyed, yet Stephen Hawking proved black holes erase it completely. We will chase glowing horizons, a wall of fire, hidden wormholes, and islands buried inside reality to find where the missing truth hides. If cosmic mysteries thrill you, a quick like and subscribe pushes this channel forward. Hold on tight. We begin. Somewhere in our galaxy, a giant star runs out of fuel. For millions of years, it burned bright, holding itself up by sheer heat. That heat pushed outward. Gravity pulled inward. The two stayed balanced, like a tug of war where neither side moves an inch. Then the fuel is gone. The outward push dies in an instant. And gravity, patient and merciless, finally wins. The core collapses. A ball of matter wider than the sun crushes down toward a single point, faster and faster, until it vanishes into something almost impossible to describe. All that mass, squeezed into a space smaller than a city, then smaller than a house, then smaller than an atom. Nothing we know of can stop the fall. What forms is a black hole. Around it hangs an invisible line called the event horizon. Think of it as a waterfall on a river. Upstream, a fish can swim in any direction it likes, but there is a point where the water rushes faster than the fish can ever swim. Cross that line, and no matter how hard you kick, you are going over the edge. The event horizon is that line drawn into space itself. Inside it, the pull is so strong that even light cannot climb back out. And light is the fastest thing in the universe, racing at 186,000 miles every second. If light cannot escape, nothing can. A rocket, a planet, a beam from a flashlight, all of it falls inward and never returns. This is why we call it black. It sits in space like a hole cut out of the night, swallowing everything that drifts too close. Now, here is the strange part. From the outside, every black hole looks almost the same. Two of them can weigh exactly the same amount and behave in exactly the same way, even if one was built from collapsing stars and the other from crushed planets, old spaceships, and 1 trillion tons of ice. Whatever falls in seems to lose its story. The horizon swallows the details and shows the world a blank face. Astronomers have now seen these monsters for real. In 2019, a team pointed telescopes across the whole planet at a giant galaxy called M87, 55 million light-years away, and captured the first true image of a black hole's shadow, a dark circle ringed by glowing gas. Proof that these things are out there, right now, feeding. The one at the center of our own galaxy weighs about 4 million times as much as the Sunday stars. Near it whip around at thousands of miles per second, yanked by a force they cannot see. Something enormous and invisible holds them on a leash. For a long time, that seemed like the whole story. A black hole is a trap. Matter falls in, the door closes, and the universe simply forgets whatever crossed the line. But a trap that perfectly forgets is a very dangerous idea, because deep in the rules of physics lives a promise the universe has kept without fail since the beginning of time, and a black hole, sitting silently in space, looks like it might break that promise wide open. To see why that terrifies physicists, we first have to meet the promise itself. The universe keeps very few promises. This is one of them. In physics, there is a rule so deep that everything else rests on top of it. Information is never truly destroyed. Whatever happens, the details of the past are always preserved somewhere, in some form, even if they become impossibly scrambled. Scientists call this idea unitarity. You can think of it as the universe's ironclad memory. Here is what that really means. Take a book and toss it into a roaring fire. The pages curl. The words vanish into smoke and ash. To your eyes, the story is gone forever. But physics says something stranger. If you could track every single particle of smoke, every wisp of heat, every speck of ash, And if you knew the exact motion of all of them, you could in principle wind the whole thing backward. The smoke would gather, the ash would rise, the pages would knit themselves whole, and the words would return, letter by letter. The information was only shuffled into a form too messy for any human to read. The story survived, hidden in the chaos. This is a promise the universe has kept in every experiment ever run. Smash particles together at nearly the speed of light, and the debris still carries the full record of what went in. Let a drop of ink spread through a glass of water until the water turns evenly blue, and every molecule still remembers where it started. In principle, the past can always be rebuilt from the present. Why does this matter so much? Because it is the reason the future can be predicted at all. The laws of physics work like a perfect machine that runs both forward and backward. Tell the machine exactly how things are today, and it can tell you how things will be tomorrow. Feed it tomorrow, and it can rebuild yesterday. That two-way street only exists if information is never lost along the way. Quantum mechanics guards this rule most fiercely of all. In the quantum world, every particle is described by a wave of possibilities. That wave carries the full story, every chance of every outcome, and the equation that steers it, written down almost 100 years ago, has a beautiful property. It only ever reshapes the wave, flowing it smoothly from one moment to the next, carrying every possibility forward intact. So, the total amount of information in the universe stays fixed, locked, conserved. It moves around, it hides, it tangles itself into knots we could never hope to untie, but the count never changes. In a very real sense, the universe cannot forget. This promise is quiet, invisible, and almost never mentioned outside a physics classroom. Yet, it holds up the entire structure of science. Break it, and prediction itself becomes meaningless. Cause and effect start to leak. The clean machine sputters and jams, and now we can feel the danger taking shape. We have a black hole, a trap that seems to swallow every detail of whatever crosses its edge. And we have a promise, sworn by the deepest law we know, that no detail can ever be lost. Both cannot be true at once. Something has to give. The first crack in the mystery appears when we ask a simple question. When matter falls into a black hole, where exactly does its story go? Throw anything you like into a black hole, and it all comes out looking identical. That sentence sounds absurd. A dictionary and a diamond are nothing alike. A star made of blazing hydrogen has almost nothing in common with a frozen comet or an old satellite. Yet drop any of them past the event horizon, and the black hole that swallows them keeps almost no record of what they were. Physicists proved this in the 1960s and 70s, and the great physicist John Wheeler gave it a memorable name. He said black holes have no hair. By hair, he meant all the little features that make one object different from another. Its shape, its color, its chemistry, the words printed on its pages. Cross the horizon, and every one of those features seems to be erased. What survives? Only 3 numbers. The first is mass, how heavy the black hole is. The second is spin, how fast it turns. The third is electric charge, though real black holes carry almost none. That is the entire description. 3 numbers, and the black hole is fully defined. Everything else about the history of what fell in appears to vanish without a trace. Think of a goldsmith melting down coins. One coin is a rare ancient piece stamped with an emperor's face. The other is a cheap modern token. Toss both into the furnace, and they melt into the same glowing liquid. Pour that liquid into a mold, and out come 2 identical gold bars. Weigh them, and they match. Nothing about the bars reveals which coin was priceless and which was worthless. The furnace kept the gold and threw away the story. A black hole seems to be the ultimate furnace. It keeps the weight, the spin, and the charge, and it discards everything else. 2 black holes can be perfect twins, even if one was born from a collapsing star, and the other from every library ever written, crushed and dropped in one book at a time. This is where the trouble sharpens, because that lost story is exactly the information the universe swore never to destroy. For a while, physicists had a comforting answer. The information, they said, is still in there. It fell through the horizon, and it is sitting inside, hidden but safe. We cannot see it from the outside, sure, but hidden is a long way from destroyed. A letter locked in a vault is still a letter. As long as the black hole exists, its secrets exist too, sealed behind the horizon like treasure at the bottom of the sea. That answer held up for years. The black hole was a vault, and the information was simply locked away, unreachable but real. The promise of the universe stayed intact, just barely. But this comfort rested on one silent assumption. It assumed the vault lasts forever. It assumed the black hole simply sits there, holding its prisoners for all eternity, never changing, never leaking, never dying. And in 1974, a young physicist in a wheelchair did a calculation that shattered that assumption completely. He found that black holes are slowly leaking, slowly shrinking, and one day they will disappear entirely. The moment black holes were allowed to die, the hidden treasure had nowhere safe to hide. The quiet mystery became a genuine crisis. To understand why, we have to go back a step, to a stubborn student who refused to believe a black hole could break the laws of heat. In the early 1970s, a graduate student had a thought that annoyed almost everyone. His name was Jacob Bekenstein, and he was worrying about a cup of hot coffee, not the coffee itself, but what would happen if he poured it into a black hole. To see why that bothered him, we need one of the oldest and most reliable laws in all of science, the law of entropy. Entropy is a measure of disorder, of how mixed up and messy something is. A neat deck of cards, sorted by suit and number, has low entropy. Shuffle it, and the order collapses into chaos. Now it has high entropy, and here is the ironclad rule. In any closed system, entropy always climbs, mess always grows. A shuffled deck never sorts itself by accident. Hot coffee always cools toward room temperature and stays there. The universe as a whole is constantly getting more disordered, and it can never run backward. This law is so trusted that scientists treat any violation as impossible. If someone claims they built a machine that lowers the total disorder of the universe, physicists know they are wrong before they even look. So, Bekenstein asked his awkward question. What happens to the entropy of that hot coffee when it falls into a black hole? The coffee is messy. It carries a large amount of disorder. But once it crosses the horizon, it is gone from view. All that remained, everyone believed, were 3 plain numbers describing the black hole, and a bare number, like mass, has no messiness to it. So it looked as though the coffee's entropy had simply been deleted from the universe. The total disorder had dropped. The unbreakable law had been broken. His teachers told him to drop it. A black hole, they said, sits outside the reach of ordinary thermodynamics, but Bekenstein refused. He decided the law must hold even for black holes, and that meant something startling had to be true. The black hole itself had to carry entropy. It had to be, in its own strange way, the messiest object in the universe. When you drop the coffee in, its disorder does not vanish. It gets added to the black hole's own disorder. The black hole grows a little, and its entropy climbs by at least as much as the coffee brought. The books balance. The law survives. But this raised a dizzying new question. If a black hole holds entropy, then entropy is really a count of hidden details, of all the ways the stuff you cannot see could be arranged. A messier object hides more information. So how much information could a black hole hide? And where, physically, was it being stored? Bekenstein chased the numbers and found something no one expected. The amount of hidden information in a black hole did not grow with its volume, with how much room there was inside. It grew with the size of its surface, with the area of the event horizon itself. That made no sense by any normal logic. If you want to store more books, you buy a bigger building with more floors and more rooms. You do not store them on the outside walls. Yet a black hole seemed to write all its secrets across its skin, and none of them in the vast space within. This strange clue would grow into one of the deepest ideas in modern physics. But first, someone had to work out what it truly meant for information to live on a surface. A black hole stores its secrets on its skin, and the size of that skin tells you exactly how many secrets it can hold. This deserves a closer look, because it hides one of the most shocking facts in physics. Imagine the event horizon as a smooth, dark sphere wrapped around the black hole. Now imagine dividing that surface into tiny squares, so small they are almost impossible to picture, each one far smaller than a single atom. Every one of those tiny squares stores exactly one piece of information. One yes or no. One bit, the smallest scrap of a fact that can exist. And the total number of bits the black hole can hold is simply the number of squares that fit across its surface. This lets us feel the sheer scale of it. The black hole at the center of our galaxy has a surface so vast that the number of bits written across it is staggering beyond comprehension. Written out, the count would be a number with about 90 digits. To put that in perspective, the number of grains of sand on every beach on Earth has only around 20 digits. The information hidden on that one horizon dwarfs every grain of sand on the planet many times over, and all of it sits on the surface, none in the middle. Here is why that shakes physicists so deeply. In everyday life, the amount of stuff you can pack into something grows with its volume. A bigger box holds more toys. A bigger warehouse holds more crates. Double the width, the height, and the depth, and you get 8 times the room inside. That is how our world normally works. Capacity follows volume, but a black hole plays by a different rule. Its capacity follows its surface area, and that hints at something almost too wild to believe. It suggests that everything happening inside a region of space can be completely captured by information written on the boundary around it. Physicists call this idea holography, after those shiny cards that show a full 3-dimensional image stored on a flat surface. Tilt the card, and the image seems to have depth, even though the surface is flat. The clue from the black hole whispered that our whole universe might work the same way, that the solid world we live in might be, in some deep sense, a projection of information stored on a distant surface. We will return to that mind-bending idea later, when it becomes the key that cracks the entire mystery open. For now, hold on to the simpler fact. A black hole is a storehouse of information, and that storehouse has a fixed, countable capacity, written across its horizon in the tiniest possible squares. This means a black hole is a real, physical object with a real, physical amount of information inside it, and that changes everything about our puzzle. If the black hole is just a vault, then its contents are safe. The information is locked away, but it endures. Yet, a vault has a temperature only if something warm is inside it, and Bekenstein's math carried a buried consequence he found deeply uncomfortable. If a black hole has entropy, then by the unbending laws of heat, it must also have a temperature. And anything with a temperature does one unavoidable thing. It glows. A glowing black hole should be impossible, and proving otherwise would fall to the most famous physicist of his age. In 1974, a 32-year-old physicist stood up and announced that black holes glow. The room did not believe him. His name was Stephen Hawking, and he had already lost most of the use of his body to a cruel disease that slowly froze his muscles. He could barely move, but his mind roamed freely across the strangest corners of the universe, and he had just done a calculation that overturned everything. For decades, the name said it all. A black hole was black. It swallowed light and gave off nothing. The idea that it might shine seemed as foolish as claiming a bottomless pit could spit things back out. Hawking had set out to prove Bekenstein wrong. He found the opposite. When he combined the physics of black holes with the rules of the quantum world, the two together produced an answer he never expected. Black holes have a temperature. They radiate. They give off a faint, steady stream of particles from their edge, drifting out into space. Today, We call it Hawking radiation. At first, this sounds like a small technical detail. It is anything but. A glowing black hole is a black hole that is losing energy. And in physics, energy and mass are two faces of the same coin, tied together by the most famous equation ever written: lose energy and you lose mass. Which means a radiating black hole is slowly, quietly getting lighter. It is shrinking. The eternal vault has a leak. To feel how strange this is, picture the deepest, coldest cave imaginable, a place where no light has ever reached. Now imagine that in the total darkness, the cave walls begin to glow, faintly, all on their own, with no fire and no lamp anywhere. That is what Hawking discovered a black hole does. The darkest object in the universe produces its own soft light, seemingly out of nowhere. The glow is unbelievably faint. For a black hole the size of the one in our galaxy, the radiation is so weak and so cold that it is colder than the empty space around it. We have no instrument on Earth remotely sensitive enough to detect it. In practice, these giant black holes look as black as ever. But faint is a world apart from non-existent. The leak is real, and once you accept that a black hole leaks, a chain of unavoidable consequences begins to unfold, each one more troubling than the last. Because if the black hole is radiating energy away, then over time it must lose all of it. Slowly, at first, then faster and faster as it shrinks, the black hole pours itself back out into space as a thin stream of particles. And eventually, after a stretch of time so long it makes the current age of the universe look like a single heartbeat, the black hole vanishes completely, gone, evaporated into nothing but a fading glow. Now hold both halves of the puzzle in your mind at once. A black hole swallows a mountain of information and locks it behind its horizon. Then, over unthinkable ages, that black hole slowly evaporates and disappears entirely. So, where does the information go? It cannot stay in the black hole, because the black hole is gone. And if it left, it must have ridden out on that faint stream of escaping radiation. Everything now depends on one question. Does the glow carry the secrets out, or does it leave them behind to die? To answer that, we have to understand how this impossible radiation is born in the first place. To understand how a black hole glows, you have to give up one comfortable idea. Empty space seethes with hidden life. We picture a vacuum as pure nothingness. No matter, no light, no motion, just still, silent void. The quantum world tells a wilder story. Down at the smallest scales, empty space is boiling. Everywhere, all the time, tiny pairs of particles flicker into existence and vanish again, faster than any clock could ever measure. They appear, they exist for the briefest possible instant, and they snuff themselves back out. Physicists call these fleeting pairs virtual particles. They come in matched sets, a particle and its opposite, born together from borrowed energy. Think of it like borrowing money from a bank with a rule that you must repay it almost instantly. The universe lets a pair pop into being on credit, as long as they wink out again and settle the debt before anyone can catch them. Out in ordinary space, they always do. The pair meets, cancels, and disappears, and the books are balanced. Now, bring this boiling vacuum right up to the edge of a black hole. A pair flickers into existence, one particle and its partner straddling the event horizon. Normally, they would find each other again and vanish. But here, at the edge of the abyss, one of the pair drifts just inside the horizon and falls in. Its partner, on the outside, is left stranded. The two can never meet again to cancel out, because one of them has crossed the line of no return. The stranded partner is now real. It escapes into space as an actual particle, part of that faint stream of Hawking radiation, and the debt still has to be paid. The energy for that escaping particle has to come from somewhere. It comes from the black hole itself. The particle that fell in carries what you can think of as negative energy, and it subtracts a tiny bit from the black hole's total. Each time this happens, the black hole loses a sliver of its mass, one flicker at a time. The boiling vacuum at the edge steals from the giant and flings a particle out into the dark. Multiply this by an unimaginable number of flickers, going on ceaselessly across the entire surface, and you get a steady glow. The black hole is being nibbled away at its edge by the restless froth of empty space itself. Here is the detail that will matter enormously later. The escaping particle and the one that fell in are born as a pair. In the quantum world, that shared birth ties them together with an invisible bond, a connection that lingers no matter how far apart they travel. The particle drifting out into space stays secretly linked to its partner trapped inside the black hole. So, the radiation streaming away is a crowd of particles, each one bound to a hidden twin behind the horizon. The outside and the inside are stitched together, thread by thread, with every particle the black hole emits. For now, keep the picture simple. Empty space bubbles with pairs. The horizon splits some of those pairs apart. Half escapes, half falls in, and the black hole pays the price by shrinking. This gentle nibbling, repeated across eons, is what slowly kills a black hole. But how fast it happens depends on a rule that turns all our instincts upside down. When it comes to black holes, the giants are almost frozen, and the tiny ones burn like nothing else in creation. The smaller a black hole gets, the hotter and wilder it becomes. And that single fact sets a countdown ticking toward a violent end. Here is a fact that feels backward every time you hear it. The bigger a black hole is, the colder it burns. In everything else we know, big and hot go together. A raging bonfire throws more heat than a candle. A giant star burns fiercer than a small one. So, you would expect a monstrous black hole, weighing millions of suns, to blaze the hottest of all. The truth runs the other way. The largest black holes are the coldest objects in existence, and the smallest are infernos. The reason comes down to the size of the horizon. A giant black hole has an enormous surface, so its escaping glow is spread thin and feeble, barely warmer than absolute zero. The supermassive giant at the heart of our galaxy has a temperature so low it is almost beyond meaning, a tiny fraction of a degree above the coldest cold there is. It leaks so slowly that it is practically frozen in time. Now shrink the black hole. As it loses mass and gets smaller, its horizon tightens and the glow concentrates. The temperature climbs. A black hole, the mass of a mountain, squeezed down to the size of a single atom, would burn white hot, blazing with radiation. And this creates a runaway. Think of a melting block of ice on a warm day. At first it melts slowly, but as it shrinks, more of its surface is exposed to the warmth for its size, so it melts faster. Smaller means faster, and faster means smaller still, until the last of it vanishes in a rush. A black hole does something similar, except the runaway grows far more extreme. As a black hole shrinks, it gets hotter. As it gets hotter, it radiates faster. As it radiates faster, it shrinks even quicker, which makes it hotter yet again. The process feeds on itself, accelerating without limit. A black hole that spent almost the entire life of the universe evaporating with agonizing slowness will burn through its final moments in a frenzy. And the very last instant is spectacular. When a black hole shrinks down to its final flicker of mass, the runaway reaches its peak. In a fraction of a second, it dumps the last of its energy all at once, in a burst as bright as millions of nuclear bombs going off together in a single point of space. After ages of near silence, the black hole ends its life in a violent flash and is gone. This tells us the fate of every black hole is sealed. The giants we see today are so cold and so slow that they will keep growing for a long while, yet feeding on gas and stars. But once the universe empties out and there is nothing left to eat, even the largest of them will begin the long slide. The colder giants hold steady, then slowly leak, then shrink, then heat, then race toward that final blinding burst. The timescale is almost impossible to grasp, and we will stare into that abyss of time in a moment. What matters right now is the ending itself. Every black hole, no matter how vast, is doomed to evaporate and detonate. None of them last forever. And that seals the trap on our mystery. The information that fell in cannot simply wait inside for eternity, because eternity is not on offer. The black hole will die. When it does, whatever it was holding must go somewhere. So the countdown is real. But just how long is it? The answer stretches the mind past its breaking point. Wait for a black hole to die, and you will wait longer than the mind can hold. We tend to think we understand big numbers. 1,000,000 seems huge. 1,000,000,000 unimaginable. The time it takes a black hole to evaporate leaves both of those in the dust so completely that ordinary words start to fail. Let us build up to it slowly. The universe right now is about 14 billion years old. That covers everything, from the first flash of the Big Bang to this very moment. Every star that ever formed, every planet, every living thing. 14 billion years. Hold that as your yardstick. A black hole, the mass of our sun, would take so long to evaporate that you would have to let the entire history of the universe replay itself again and again. A number of times so large it has over 50 digits. The age of the cosmos, run start to finish, more times than there are atoms in a mountain, and only then would that modest black hole finally fade away. And the giant at the center of our galaxy, weighing 4 million suns, takes vastly longer still. Its lifetime is a number so enormous that writing it out would fill line after line with zeros. Compared to it, the current age of the universe is less than the blink of an eye, less than the first flicker of the first instant. We are, in a sense, still living in the black hole's opening breath. To feel this, imagine a single drop of water falling into a bucket once every billion years. One drop every billion years. You would fill an entire ocean, drop by patient drop, and still not come close to the time it takes the largest black holes to disappear. The scale is so vast that our language simply runs out of room. For nearly all of that unthinkable stretch, the black hole barely changes. It sits in the growing dark, leaking so slowly that from moment to moment it looks utterly still. Stars burn out, galaxies drift apart. The universe grows cold and empty and quiet, and through all of it, the black hole waits, shedding its mass one faint particle at a time, so gradually that 1,000,000,000,000 years is nothing to it. Then, at the very end, after ages beyond counting, everything speeds up. The black hole finally shrinks small enough for the runaway to take hold. The slow leak becomes a torrent. The last of the mass pours out, and in a final blinding flash, the ancient giant that outlasted every star in the sky is gone in less than a second. This is the strangest funeral in the universe, a near eternity of stillness, ended by a heartbeat of fire. But this is the part that matters for our mystery. The black hole does not last forever after all. Given enough time, and time is the one thing the universe has in endless supply, every black hole evaporates completely. The vault does not just leak, it empties itself entirely and then ceases to exist. So, the comforting old answer is finished. We can no longer say the information is safely locked inside, because there will come a day when there is no inside left. The horizon closes over the secrets, the black hole slowly burns away, and at the end, there is nothing but a puff of fading radiation drifting off into the dark. Everything now hangs on that radiation. It is the only thing that survives. If the secrets escaped at all, they escaped in that glow. So the whole mystery narrows to a single, sharp question. What exactly does the glow remember? Hawking looked closely at the glow leaking from a black hole, and what he saw drained the color from his face. The escaping radiation, he realized, is almost perfectly featureless. It depends on only one thing, the mass of the black hole. Tell me how heavy a black hole is, and I can tell you everything about the light it gives off, the colors, the pattern, the energy. Two black holes of the same weight glow in exactly the same way, no matter what fell into them. Feed one black hole, a library of every book ever written. Feed another black hole of the same weight, a cloud of plain hydrogen gas. According to Hawking's math, both of them glow identically. The radiation carries no fingerprint of the books, no echo of the gas, no hint of the difference. The glow is the same either way. The best comparison is the static hiss on an old television tuned to a dead channel. That grey snow is pure random noise, empty of any picture or message. You could stare at it forever and never pull a single word out of it, because there is nothing there to find. Hawking's radiation looked exactly like that. Meaningless snow streaming out of the black hole, hissing the same way whether the black hole ate an encyclopedia or a puff of smoke. This is called thermal radiation, and it is the plainest, most forgetful kind of light there is. It is the glow of pure heat, and heat remembers nothing about where it came from. A red-hot poker glows the same whether you heated it in a wood fire or an electric coil. The light of raw temperature erases the story of its source. Now put the two halves of the mystery together and feel the trap slam shut. A black hole swallows an ocean of information. Its horizon holds a record with more digits than there are grains of sand on every beach on Earth. Then the black hole spends an eternity slowly evaporating, giving all of itself back to the universe as a stream of glowing particles. And that stream, Hawking found, is featureless static that carries none of the swallowed information out with it. When the black hole finally vanishes in its last bright flash, the radiation drifts away as meaningless noise, and the record is nowhere. It is gone from the inside, because there is no inside anymore. It is gone from the glow, because the glow was blank. The information is simply erased from the universe, as if it had never existed. And this is the paradox in its full, terrible form. The deepest promise in all of physics says information can never be destroyed. The universe keeps a perfect memory, but a black hole appears to take that memory, hold it for an age, and then wipe it out completely, leaving nothing behind but forgetful heat. Both statements cannot be true. Either the promise is broken, and the universe can forget after all, or Hawking missed something, and the glow secretly carries the secrets out in a way too subtle for his calculation to catch. Hawking himself, staring at his own math, came down hard on one side, and the answer he chose would ignite the longest and fiercest argument in modern physics. In 1976, Stephen Hawking wrote down a claim so bold it amounted to rewriting the rulebook of reality. He had followed his own calculation to its end, and he refused to flinch from where it led. If black holes glow with featureless radiation, and if that radiation carries none of the swallowed information out, then the conclusion was plain. When a black hole evaporates, the information inside it is destroyed, truly, permanently, gone. Most physicists would have assumed they had made a mistake somewhere. The promise that information cannot be destroyed was so sacred that breaking it felt unthinkable. But Hawking turned the logic around. His calculation, he argued, was solid. It combined gravity and the quantum world carefully and correctly. If it clashed with the old promise, then perhaps the old promise was the thing that had to go. He was pointing a finger straight at the beating heart of quantum mechanics. Recall the crucial rule. In the quantum world, everything is described by a wave of possibilities that always flows smoothly, never losing a scrap of information along the way. This is what guarantees the universe never forgets. Physicists trusted it completely. Every experiment ever performed had obeyed it without a single exception. Hawking's claim shattered that trust. He was saying that inside a black hole, the sacred rule breaks. A black hole takes a clean, complete quantum description of everything that fell in and grinds it into featureless noise. The rich, detailed wave that entered comes out as blank static. Information that should have been perfectly preserved is smeared into nothing. To picture the crime, imagine a shredder that does the impossible. Ordinary shredders slice paper into strips, but the strips are still there. Tape them back together with enough patience, and you recover the page. Hawking's black hole was a shredder that made the strips themselves vanish. The pieces were gone from reality itself, wiped out of existence entirely. You could search the whole universe forever and never reassemble the page because there was nothing left to find. This was a staggering thing to propose. Hawking carried enormous authority. He was among the greatest minds alive, a man who had already transformed our understanding of black holes. When he said quantum mechanics itself might need rewriting to allow for lost information, people had to take it seriously, however much it horrified them. And horrify them it did, because Hawking was proposing that the universe has holes in its memory, that in certain places, under certain conditions, the past can be genuinely erased, leaving no trace anywhere for anyone to recover. For a while, Hawking held his ground with total confidence. He believed the information was gone, and he was prepared to sacrifice one of the deepest principles in science to say so. He even suggested new equations that would allow information to leak out of the universe entirely, a modified quantum mechanics built to permit forgetting. Many physicists were quietly furious. They were certain Hawking had to be wrong, that the information had to survive somehow. But they had a serious problem. Nobody could find the flaw in his reasoning. His calculations stood there, stubborn and unbroken, insisting that black holes destroy information. The battle lines were drawn. On one side, Hawking and his shredded, forgetful universe. On the other, a crowd of physicists clinging to the promise that the past can never truly die. And to understand why they were willing to fight so hard, we have to see just how much would collapse if Hawking turned out to be right. If Hawking was right, and information can be destroyed, then far more than one rule falls. The entire clockwork of reality begins to seize up. To see why, picture the universe as a perfectly reliable machine. Feed it the complete state of everything at one moment, every particle, every position, every motion, and the laws of physics grind forward and tell you exactly what comes next. Run the machine backward, and it rebuilds the past just as precisely. This two-way certainty is the quiet foundation under all of science. It is the reason we can predict an eclipse centuries early, or trace light from a distant galaxy back to its birth. That whole machine runs on one requirement: information must be conserved. The present has to hold the full record of the past, and it has to fully determine the future. Snip that thread, and the machine no longer works in either direction. Now let black holes destroy information, as Hawking claimed. Suddenly there are events in the universe with no traceable cause. A black hole evaporates, and the record of what fell in is erased. Look at the fading radiation afterward, and you cannot reconstruct what came before. The past has a blank spot, a wound with no way to see through it. And this poison does not stay politely inside black holes. Tiny black holes can, in principle, flicker into existence and evaporate away in the boiling froth of empty space, everywhere, all the time. If each one destroys a little information as it goes, then reliability leaks out of physics everywhere at once. Predictions would carry a faint, incurable fuzziness, not just near black holes, but in every corner of creation. Some physicists found an even sharper problem. When they tried to write down equations that let information vanish, the math bit back. It seemed to break the conservation of energy, another law so trusted that violating it is almost the definition of impossible. In some versions, a universe that could forget would also start heating up wildly, pumping out energy from nowhere. The whole thing threatened to spiral into nonsense, so the stakes could not have been higher. Accepting Hawking's answer meant accepting a universe where cause and effect fray at the edges, where the past can rot away, where prediction itself carries a permanent crack. For most physicists, that was a price too terrible to pay. Think of it like discovering that a single grain of sand, under the right conditions, could make 1 + 1 = 3. It would be a catastrophe. It would mean arithmetic itself could no longer be trusted, and every calculation ever made would fall under suspicion. Hawking's lost information threatened math and physics in just that way. One exception, and the whole structure trembles. This is why so many brilliant people refuse to let it go. They were fighting for something precious. They could feel, correctly, that if the universe truly forgets, then the deepest dream of science, the dream of a fully knowable, fully predictable cosmos, dies with it. And so a strange standoff settled over physics. Hawking's calculation said information dies. The foundations of science screamed that it cannot. Both sides had powerful reasons, and neither could defeat the other. For a problem this fierce, sometimes the only way forward is to force the question into the open. And that is exactly what three physicists did, by turning the whole paradox into a wager with a very unusual prize on the line. In 1997, three of the sharpest minds in physics did something playful about the most serious question of their careers. They made a bet. On one side stood Stephen Hawking and a fellow physicist named Kip Thorne. They wagered that Hawking was right, that information falling into a black hole is destroyed for good. On the other side stood John Preskill, a quantum physicist who was certain the information survives. He bet that somehow, some way, the secrets escape. The stakes were charmingly small for such a cosmic quarrel. The loser would buy the winner an encyclopedia, a book stuffed with information, from which any fact could be looked up at will. The joke was obvious and pointed. An encyclopedia is a machine for recovering information on demand, the very thing they were fighting over. This kind of wager was a Hawking trademark. He loved betting on the deepest puzzles in physics, partly for fun, and partly because a public bet forces everyone to state plainly what they believe and why. It turns a vague disagreement into a sharp, recorded stand. Now, the paradox had two famous names attached to each answer, and the whole field was watching to see who would blink. For years, neither side could land a knockout blow. Hawking's calculations still stood, insisting on destruction. But on the other side, the ground was quietly shifting. New ideas were taking shape, strange tools borrowed from the far edges of physics, and they were beginning to hint that Preskill might be right after all. That information could escape a black hole if only physicists could work out the mechanism. Then, in 2004, came a moment that stunned the physics world. At a major conference, before a packed room and a crowd of reporters, Stephen Hawking stood up and conceded the bet. He announced that he had changed his mind. After nearly 30 years of insisting that black holes destroy information, he now believed the information gets out. His original calculation, he admitted, had missed something. The black hole does not erase the past, after all. In some subtle, tangled way, the secrets leak back into the universe as the black hole fades. True to the terms, Hawking handed Preskill his prize, an encyclopedia of baseball, and joked that perhaps he should have just given him the ashes. The image was perfect. The man who once claimed the universe could forget, now paying his debt with a book from which any fact can be recovered. But here is the twist that keeps this story honest. Hawking conceding was only a gesture, a public change of heart from a great physicist who now trusted that information survives. What it lacked was the crucial thing, a clear, convincing explanation of how the information escapes. Hawking believed the paradox was solved in spirit. The detailed machinery was still missing. Thorne, his fellow bettor, refused to concede at all. He was not convinced the case was closed, and strictly speaking, he was right. The bet was paid, but the mystery was still open. Everyone now suspected the information gets out. Almost nobody could yet say exactly how. To find the how, physicists had to reach for one of the strangest phenomena in all of nature, a ghostly connection between distant particles that Einstein himself called spooky, and that hides at the very center of the black hole puzzle. To crack the paradox, we first have to understand entanglement. Two particles can be born so deeply connected that touching one instantly tells you about the other, even if they sit on opposite sides of the galaxy. This is entanglement, and it is one of the strangest truths the quantum world has ever handed us. Einstein hated it. He called it spooky action at a distance and spent years trying to prove it could not be real. Every experiment since has proven him wrong. Entanglement is real, and it may be the thread from which the whole universe is woven. Here is the basic idea. In the quantum world, a particle often has no definite answer to a question until you actually measure it. Take a property like spin, which you can loosely picture as a particle pointing up or down. Before you look, the particle is genuinely undecided, holding both possibilities at once until the moment of measurement forces it to choose. Now make two particles together in a special way, so their fates are linked. Send them flying far apart. One to your left hand, one carried to the far end of the solar system. Neither one has settled its answer yet. Both are still undecided, but they are bound by a rule. Whatever one turns out to be, the other must be the opposite. Measure your particle, and it snaps to a choice. Say, up. In that instant, its distant partner is forced to become down, no matter how far away it is. The two agree perfectly, every single time, faster than any signal could possibly travel between them. Picture a pair of magic coins. You seal each one in a box and send the boxes to opposite ends of the country. Neither coin has landed on heads or tails yet. Both are spinning in a blur inside their boxes. The moment you open your box and your coin falls heads, the other coin, hundreds of miles away, instantly falls tails. Open 1,000 such pairs, and they match as opposites every time, with no wires, no messages, no way for one to tell the other what to do. That is the heart of entanglement, a shared connection so tight that the two particles behave like a single object, even when a whole galaxy lies between them. They share one joined answer that only fills itself in when someone finally looks. This connection is real, measurable, and used every day now in the first quantum computers and quantum codes. It is one of the best tested facts in all of science, and it sits at the very center of the black hole puzzle. Because remember what Hawking discovered about the birth of his radiation. Every particle that escapes a black hole is born entangled with a partner that falls inside. The glow drifting away is tied, thread by thread, to the darkness within. Each escaping particle carries an invisible bond reaching back across the horizon to its trapped twin. For a single particle, that is no trouble at all. But a black hole does not emit one particle. It emits an ocean of them, over an unthinkable span of time. And as those entangled threads pile up year after year, they build toward a contradiction that should never be allowed to happen. To see it, we have to count the threads. Count the invisible threads tying a black hole's glow to its interior, and you find a number that climbs and climbs until it snaps. Follow a black hole across its long life. In the early days, it emits a little radiation. A handful of particles drift out, each one entangled with a partner that fell inside. So far, everything is fine. The black hole is huge. It has room to spare for all those trapped partners, but the radiation never stops. Particle after particle streams away, over millions, then trillions, then unthinkable stretches of years. And every single one of them adds another thread of entanglement reaching back through the horizon. The connection between the outside glow and the inside darkness grows steadily stronger, thread by thread, without pause. Here is the measure that matters. Physicists track the total entanglement between the escaping radiation and the black hole, and they can put a number on it. In Hawking's original picture, that number only ever climbs. The longer the black hole radiates, the more tangled the outside becomes with the inside. The bond keeps growing, apparently forever. Now recall what we learned earlier. A black hole is shrinking the whole time it radiates. Every particle it emits carries away a sliver of its mass. So while the entanglement with the outside keeps rising, the black hole itself keeps getting smaller. And a smaller black hole has a smaller horizon, which means it can hold less information. Its storage is shrinking. Feel the collision coming. The entanglement between the radiation and the black hole rises without limit. But the black hole's ability to store entanglement falls as it shrinks. Two lines heading in opposite directions, one climbing, one dropping. Sooner or later, they cross. And past that crossing point, Hawking's picture demands something flatly impossible. It demands that a tiny black hole, with room for only a little information, stay entangled with a vast ocean of radiation far larger than itself. It is like asking a thimble to stay tied to the entire sea, when the thimble has room for only a few drops. The books cannot balance. The math breaks. Think of it as a rope with more and more strands being tied to a shrinking post. At first, the post is a mighty tree trunk, easily anchoring every strand, but the post is being whittled down even as the strands multiply. Eventually, you are trying to anchor 1,000 heavy ropes to a toothpick. The toothpick cannot hold. Something has to give. This is the paradox seen from inside the mathematics. Hawking's calculation, followed faithfully, leads to a state that quantum mechanics forbids. An impossible amount of entanglement tied to an object far too small to carry it. The numbers themselves are screaming that the story cannot be right. So one of two things must be true. Either quantum mechanics really does break near a dying black hole, exactly as Hawking first claimed, or his calculation goes wrong somewhere along the way, and the true amount of entanglement does something his math never allowed, something that keeps the books balanced, something that lets the black hole let go of the outside before it is too small to hold on. A physicist named Don Page stared hard at this collision, and he asked a simple, powerful question. If the universe is sane, and information really does survive, then what shape must that rising entanglement actually take? His answer drew a curve that would become the single most important graph in the entire mystery. Don Page realized that if information escapes a black hole, the entanglement cannot rise forever. At some point, it has to turn around and fall. Page trusted the promise. He believed quantum mechanics holds, that information survives, that the universe never forgets. And he asked what that belief demands of the glow leaving a black hole. He was tracking the entanglement between the escaping radiation and everything left behind, and he worked out the exact shape that number must follow over the black hole's entire life. Picture a graph. Time runs along the bottom, from the black hole's birth to its final flash. The height of the line shows how entangled the radiation is with the black hole. Now watch what Page's reasoning says the line must do. At the start, the black hole has emitted almost nothing. The entanglement is near zero. As radiation begins to stream out, the line rises. Early on, this matches Hawking exactly. Each escaping particle deepens the tangle between outside and inside, and the line climbs steadily upward, just as everyone expected. But then, if information truly survives, the line does something Hawking's math never allowed. It reaches a peak, it stops climbing, and then it bends back down and begins to fall, dropping steadily until it reaches zero again at the very moment the black hole disappears. The whole shape looks like a mountain, up one side, over the summit, and down the other. Physicists call it the Page curve, and it is the fingerprint of a universe that keeps its promise. If the entanglement traces that mountain, then information is being preserved. If it climbs forever, without turning, like a staircase to nowhere, then information is being destroyed. Why must the line come back down? Because of what a falling entanglement actually means. When the tangle between the radiation and the black hole starts to shrink, it is a sign that the radiation is beginning to carry real information, secrets that are leaking back out into the escaping glow. By the time the line hits zero, every last thread has been untied. The black hole is gone, and all its information has been handed back to the universe, woven into the radiation drifting away. So the two pictures give two completely different mountains. Hawking's line is a ramp that only goes up and then falls off a cliff at the end, when the black hole suddenly vanishes and takes its secrets with it. Page's line is a smooth mountain that rises, peaks, and gently returns to the ground, carrying every secret safely out along the way. The difference between them is the difference between a universe that forgets and a universe that remembers. Two curves, one question, and for decades, nobody could prove which one nature actually draws. Page could describe the shape the curve must take if information survives. What he could not do was show, from the raw physics of a black hole, why the line ever turns around. Hawking's calculations still insisted it climbs forever. Page's demand that it come back down was a statement of faith in quantum mechanics, beautiful and clear but unproven. The whole paradox now had a precise target. Forget vague arguments about lost secrets. The real challenge was sharp and mathematical. Make the line bend, show, from the actual laws of nature, why the rising entanglement reaches a peak and falls. And that peak, the exact moment the mountain turns, hides a secret of its own, a special instant in the black hole's life, halfway through its death, when everything changes. Halfway through a black hole's long death, a hidden switch flips, and the secrets begin to escape. That halfway point has a name. Physicists call it the Page time, and it marks the summit of the mountain, the exact instant the entanglement stops rising and starts to fall. Before it, the black hole seems to hoard its information. After it, the information starts flowing back out into the glow. Everything hinges on this single turning point. But halfway measured how? Here is the surprising part. The Page time is measured in information, not on a clock. It arrives when the black hole has given up about half of its total entropy, half of its hidden information capacity, to the radiation streaming away. Because of the wild way black holes speed up as they shrink, this moment comes long before the black hole is halfway to death in ordinary time. But in terms of information, it is the true midpoint, the balance point of the whole story. Think of the black hole as a locked diary slowly burning at the edges. For the first half of the burning, the flames only consume blank margins, and the pages that drift away as smoke carry nothing you could read. Then you pass the halfway mark. Now the flames begin to reach the written pages themselves. Every wisp of smoke that rises from here on carries fragments of the actual words. If you were clever enough to catch and read the smoke, you could slowly piece the diary back together as it burns. That is what the Page time means. Before it, the escaping radiation is essentially blank, carrying no recoverable secrets. After it, each new particle that leaves begins to carry real information about what fell in, until the final flash releases the last of it. This gives physicists a strange and powerful prediction. If you could collect every particle a black hole emits, and if you had already gathered more than half of them, then hidden inside that pile of radiation would be a complete, recoverable record of everything the black hole ever swallowed. The secrets would be there, scrambled and spread across countless particles, but fully present, waiting to be decoded. And this leads to one of the most mind-bending ideas in the whole saga. After the Page time, the radiation outside and the black hole inside are so deeply linked that the information about what fell in becomes readable from the outside alone. The inside of the black hole and the distant glow start to behave like two copies of the same secret. Reach into the radiation, and you are, in a strange sense, reaching into the heart of the black hole itself. That should be impossible. The inside of a black hole sits behind a horizon that nothing can cross back over. How can its secrets be sitting out in the radiation, light years away, at the very same time? It sounds like the information is in two places at once, inside the black hole and outside in the glow. And that violates one of the most basic rules of the quantum world. For years, this was where the trail went cold. Physicists could see that the Page curve had to bend, that the Page time had to exist, that the information had to come out. But every attempt to explain how ran straight into a wall of contradictions. The math would not cooperate. The paradox seemed to mock every solution. To break through, physicists would have to question something they had never dared to doubt. The idea that an object can only ever be in one place at one time. And the first crack in that wall came from a wild proposal that sounded more like a riddle than a theory. Here are chapters 18 through 33, closing out the full arc from the first wild fix, all the way to space-time itself being woven from entanglement. The first escape from the trap was a riddle. What if the information is inside the black hole and outside in the radiation at the same time, and nobody is ever allowed to check both? This idea came from a physicist named Leonard Susskind, along with a few others, in the early 1990s. They called it black hole complementarity, and it asks you to accept two descriptions of the same event that seem to flatly contradict each other. Imagine an astronaut falling into a black hole while a friend watches from a safe distance far away. Ask what happens to the astronaut, and you get two completely different answers, depending on who you ask. From the falling astronaut's own point of view, crossing the horizon is a quiet non-event. There is no wall, no barrier, nothing to feel. She sails across the invisible line and continues inward, carrying all her information with her, straight into the black hole. For her, the secrets go in. From the distant friend's point of view, something else entirely happens. Because of the strange way time warps near a black hole, the friend never sees the astronaut cross the horizon at all. Instead, she appears to slow down, freeze, and smear across the surface, getting fainter and hotter until she is absorbed into the horizon and radiated back out. For the friend, the secrets stay outside, plastered onto the surface, and eventually leak away in the glow. So, which is it? Does the astronaut's information fall inside, or does it stay outside? Complementarity gives a slippery answer. Both. It says each description is completely correct for the observer who holds it. And here is the trick. No single observer can ever see both at once. The friend can watch the information smeared on the surface, but can never reach inside to check on the astronaut who fell in. The astronaut can experience herself sailing safely inward, but can never send a message back out to the friend. The two accounts describe the same reality, yet the universe is arranged so that nobody can ever stand in a place to catch them contradicting each other. Picture a fish in a bowl and a cat outside it. The fish reports that the world is a bright, watery sphere. The cat reports a small glass ball on a table. Both are right about the same bowl. Neither can ever climb into the other's viewpoint to force a showdown. Complementarity claimed the black hole works like this. Two truths, kept forever apart, so they never openly clash. It sounds like a cheat, and in a way, it is a very bold gamble. It bets that the universe will always protect itself, that the laws are arranged so no observer ever catches the contradiction red-handed. As long as that holds, information can be preserved for the outside world without the inside astronaut ever noticing anything strange. For years, this clever dodge held the line. It let physicists believe the information survives, smeared onto the surface and carried out in the radiation, while the person falling in feels nothing unusual. The paradox seemed to be soothed, if not truly solved, but the idea rested on a picture of the horizon as something almost solid, a hot surface that could hold information pressed against it. And that picture raised a fresh and troubling question. What exactly is sitting at the horizon, holding all those secrets in place? If information smears across the surface of a black hole, then the surface must be something real enough to hold it. Physicists gave that something a name, the stretched horizon. The stretched horizon is a thin shell hovering just above the true event horizon, unimaginably close to it, a hair's breadth outside the line of no return. And in this picture, it is not a calm, empty boundary. It is a seething, blazing membrane, hotter than anything you can picture, crackling with activity. Think of the true event horizon as the exact edge of a waterfall, the precise line where the water starts to fall faster than any escape. The stretched horizon is the churning, roaring band of spray and foam just above that edge, where everything is violent motion. In this view, that thin band of chaos is where a black hole stores and processes its information. Here is how it works. When the falling astronaut approaches, the distant friend sees her hit this searing membrane. Her information gets absorbed into the frenzy, scrambled together with everything else already there, cooked into the churning surface. Then, particle by particle, the membrane radiates that information back out in the escaping glow. The stretched horizon acts like a hard drive made of pure fire, taking in every secret, mixing it beyond recognition, and slowly beaming it away. This gave complementarity a physical home. The two truths could coexist because the stretched horizon did the work. For the outside friend, the astronaut is absorbed and re-radiated by this hot shell. For the astronaut herself, she feels nothing, because the searing membrane is only how the outside world describes her, not something she runs into on her own way down. And this membrane is a champion scrambler. Physicists worked out that a black hole is the fastest scrambler of information in the entire universe. Drop a secret onto the stretched horizon, and it spreads and mixes across the whole surface faster than any other object in nature could manage. Nothing shuffles information more thoroughly or more quickly than a black hole. It takes a clear message and smears it across its surface almost instantly, hiding it in plain sight. That extreme scrambling was a comfort. It meant the information really could come out in the radiation, just so hopelessly jumbled that Hawking's calculation, which only measured the average, would see nothing but featureless static. The secrets would be there, spread across countless particles in a code so tangled that no simple measurement could catch them. Picture a message written on a single drop of ink, then that drop stirred into an entire swimming pool. The ink is still there. Every molecule of the message survives, spread through the water. But you would never read it by scooping up a single cup. You would need to track every molecule in the whole pool to reassemble the word. The stretched horizon does this to information, and the escaping radiation carries the scattered ink away. For a while, this felt like real progress. The information survives, scrambled on a hot membrane, radiated out in a code too complex to easily read. Complementarity plus the stretched horizon seemed to keep the promise intact, but the whole scheme rested on a deeper foundation that nobody had fully justified. It quietly assumed that everything inside a region of space could be described entirely by what sits on its boundary, and proving that turned out to require one of the most revolutionary ideas in the history of physics. The clue, hiding in every black hole, pointed to something almost too strange to believe. Our three-dimensional world might be a projection of information stored on a distant, flatter surface. This is the holographic principle, and it grew directly out of Bekenstein's old discovery that a black hole's information lives on its surface, counted by area rather than volume. Physicists took that oddity and pushed it to a breathtaking conclusion. Perhaps everything works this way. Perhaps any chunk of space can be fully described by information written on the boundary that surrounds it. The name comes from the shiny holograms you have seen on credit cards, flat surfaces that store a full three-dimensional image. Tilt the card, and depth appears out of a film with no thickness at all. The holographic principle says the universe pulls off the same trick, but for real, a flat surface, storing every detail of the solid space within. In 1997, a physicist named Juan Maldacena turned this dream into hard mathematics. In one of the most important discoveries of modern physics, he found a precise, exact example where the trick provably works. He described a particular kind of universe, a region of space with gravity and black holes and everything inside it, and showed that it is perfectly mirrored by a completely different physics living on its distant boundary. The inside has gravity and extra dimensions. The boundary is flatter, with no gravity at all, just particles interacting on a surface. And yet the two descriptions are exactly the same physics, written in two different languages. Anything that happens inside can be translated into something on the boundary, and back again, with nothing lost. Two worlds, one reality, connected by a perfect dictionary. This is called a duality, and it is one of the deepest ideas ever found. It says gravity and curved space on the inside are secretly identical to ordinary particles dancing on a flat edge. The bulk and the boundary are two faces of one thing. Think of a video game world. On your screen, there are mountains, caves, characters, and space stretching into the distance. But all of that richness is really stored as flat code on a chip, a stream of information with no mountains in it at all. The world you see and the code that generates it are the same thing in two forms. Maldacena showed that a universe with gravity can relate to its boundary in exactly this way, with the boundary as the code and the inside as the picture it produces. Why does this matter so much for our black hole? Because it hands physicists something priceless. A place where a black hole, with all its paradoxes, is described by boundary physics that everyone already trusts. And on that boundary, there are no mysteries about lost information. The boundary is ordinary quantum mechanics, and ordinary quantum mechanics never forgets. Information there is always preserved, without question. So, if the inside really is the same as the boundary, and the boundary never loses information, then the black hole inside cannot lose information either. The holographic dictionary guarantees it. The secrets that fall in must come back out, because the boundary version of the story keeps perfect track of every one of them. This was a stunning turn. It meant that somewhere, in the deep structure of physics, the paradox had to have an answer. The promise was safe. But knowing the information survives is different from seeing how it climbs back out of a black hole. To watch that happen, physicists first had to read the black hole itself as a hologram. If the holographic dictionary is real, then a black hole is a message written on its own surface, and the volume inside is a picture that surface paints. This flips our whole intuition about black holes upside down. We have been imagining the black hole as a deep well, with information falling down into a vast interior. Holography says look at it the other way. The true description lives on the horizon, that thin, two-dimensional skin, and everything we think of as the inside, the depth, the plunge toward the center, is a kind of projection conjured up by information stored on the surface. On this view, when the astronaut falls in, her information does not simply vanish into a bottomless pit. It gets encoded onto the horizon, written into the surface in a scrambled form. The interior she experiences, the sense of falling deeper, is a shadow cast by that surface data. The black hole is a hologram, and the inside is the image it projects. This gave physicists a powerful new way to track information. On the boundary, everything obeys plain quantum mechanics, so they could follow the astronaut's secrets on the surface, where the rules are clear and information is never lost, and trust that whatever the surface says must also be true of the inside. The confusing interior could be understood through the trustworthy skin, and it explained the stretched horizon's role in a deeper way. That hot, scrambling membrane was really the surface, doing its job as a hologram, taking incoming information, encoding it into surface data, and eventually beaming it out. The membrane was the black hole's true self, and the yawning interior was the story that membrane told. Here is a way to picture it. Think of a shadow puppet show. On the wall, you see dragons and castles moving through deep, dramatic scenes, but all of it is produced by flat cardboard cutouts held near a light. The rich three-dimensional drama on the wall is generated entirely by simple two-dimensional shapes. Holography says the black hole's cavernous interior is the drama on the wall, and the horizon is the set of cutouts that produce it. This reframing turned the paradox into something more manageable. The question was no longer the mysterious inside of a black hole, a place hidden forever behind a horizon. It became a question about information on a surface, obeying rules physicists understood well. And on the surface, there was every reason to believe the page curve would bend the right way. But believing and proving are far apart. Even with holography in hand, even knowing the information must survive, physicists still could not point to the mechanism. They could not show, step by step, how the entanglement peaks and falls. The dictionary promised an answer existed. Reading that answer out of the equations was another matter entirely. And worse, this new confidence walked straight into a nightmare, because if you take the idea seriously that information smears onto the horizon and comes back out in the radiation, and you combine it with what we learned about entanglement, you can build an argument so sharp that it seems to prove the falling astronaut does not sail peacefully across the horizon at all. Instead, she slams into a wall of fire and is burned to nothing at the very edge, and that horrifying possibility nearly tore the whole field apart. In 2012, 4 physicists published an argument so disturbing that it split the community in two. They claimed that anyone falling into a black hole would be incinerated the instant they touched the horizon. Their names gave the idea its nickname. The 4 were Almhiri, Marolf, Polchinski, and Sully, and the terror they described came to be called the firewall, a blazing sheet of energy sitting right at the horizon, ready to burn any traveler to ash the moment they crossed. This flew in the face of everything Einstein taught. His theory of gravity says the horizon of a large black hole is a perfectly ordinary place. Nothing special marks it. A falling astronaut should sail across without feeling a thing, exactly as complementarity had promised. The horizon is smooth, empty, unremarkable. That was the settled wisdom for decades. The firewall argument said that settled wisdom leads to a contradiction and something has to break. Here is the chain of reasoning that forced the horror into the open. Take a black hole that has already passed its halfway point, its page time. By now, we learned, each new particle it emits must carry real information out, which means each new particle must be entangled with all the radiation that escaped earlier. That entanglement with the earlier glow is what lets the information come out. It is required for the promise to hold. But recall how Hawking radiation is born. Each escaping particle is also entangled with its partner just inside the horizon. That inside entanglement is what makes the horizon smooth and empty, what lets the astronaut fall through unharmed. It is required for the horizon to feel like nothing. Now the trap springs. The escaping particle needs to be fully entangled with 2 different things at once. With the old radiation far away, to carry the information out, and with its partner inside, to keep the horizon calm. And there is a deep law of the quantum world that says this is forbidden. A particle cannot be fully entangled with 2 separate partners at the same time. Something has to give. The firewall crew argued that the entanglement with the old radiation wins because the information must come out, which means the entanglement with the inside partner has to be broken, and breaking that bond has a violent consequence. It floods the horizon with enormous energy, turning the smooth, empty edge into a searing wall of fire. So the astronaut does not drift peacefully across after all. She hits a firewall and is destroyed on contact, right at the boundary. This was a catastrophe for physics. It meant giving up one of Einstein's most cherished predictions, that the horizon of a big black hole is a gentle, ordinary place. It pitted the deepest rule of quantum entanglement against the deepest rule of gravity, and the two would not both fit. One of the pillars had to fall. Picture standing at a doorway that 2 trusted friends describe completely differently. One swears it is an open, empty frame you can walk through freely. The other swears it hides an invisible furnace that will burn you alive. Both friends have never been wrong before. That was the firewall. 2 flawless lines of reasoning, pointing at the same horizon, giving answers that could not both be true. At the very center of this clash sat that one iron law about entanglement, the rule that a particle cannot fully bond with 2 partners at once. To understand why the firewall felt so inescapable, we have to look hard at that law. There is a rule in the quantum world as strict as any promise the universe keeps. A particle can be fully entangled with only 1 partner at a time. Physicists call it the monogamy of entanglement. The word monogamy is chosen on purpose. Entanglement, at its deepest, behaves like an exclusive bond. If 2 particles are completely, perfectly entangled with each other, then neither of them has any entanglement left to share with anyone else. Their connection uses up all of it. A 3rd particle simply cannot squeeze in and share that same total bond. The link is spoken for. This is not a vague guideline. It is a hard mathematical fact, proven from the core rules of quantum mechanics and tested in laboratories. When 2 particles share a maximal entanglement, that connection is theirs alone. Any bond either one forms with a 3rd party must be weaker, partial, a lesser thing, Full entanglement cannot be split three ways. Here is a way to feel it. Imagine entanglement as a certain fixed amount of trust that a particle has to give. If it pours all of that trust into one partner, holding nothing back, there is simply none left over for anyone else. It can spread its trust thinly among several partners, a little here, a little there. Or it can pour everything into one. It cannot pour everything into two. The total is fixed, and giving all of it to one leaves zero for the rest. Now you can feel exactly why the firewall argument bites so hard. After the page time, each freshly escaping particle is asked to do the impossible. It must be fully entangled with the great cloud of old radiation so that information can leak out, and it must be fully entangled with its partner just inside the horizon so that the horizon stays smooth and empty. Two full bonds, demanded at once, from a single particle. Monogamy forbids it flatly. The particle cannot give all its trust to the old radiation and all of it to the inside partner. One of those bonds has to break, and whichever one breaks, something precious shatters. Break the bond with the old radiation, and information is lost, and Hawking wins after all. Break the bond with the inside partner, and the horizon erupts into a firewall. This is the real engine underneath the whole crisis. It is not a vague worry. It is a sharp, provable conflict between three things. Physicists trusted absolutely that information escapes, which demands one entanglement, that the horizon is smooth, which demands another, and that entanglement is monogamous, which says you cannot have both. Three trusted truths, and they cannot all stand together. That is what made the firewall so hard to dismiss. Every attempt to wave it away ran into this same iron rule, blocking the exit. For years, the field was stuck at this crossroads, staring at a choice nobody wanted to make. On one path, the horizon becomes a wall of fire, and Einstein's smooth space-time is wrong. On the other, information dies inside black holes, and quantum mechanics is wrong. Two roads, both leading off a cliff. To escape, physicists needed a way to satisfy monogamy without picking either disaster. They needed the entanglement to somehow rearrange itself, so the escaping particle could stay bonded to the inside and still hand its information to the outside. And the idea that finally cracked it open sounded, at first, completely insane. The whole of physics had backed itself into an impossible corner: burn the astronaut at a wall of fire, or let the universe forget. Two answers, both unthinkable, and no third door in sight. Let us stand in that corner for a moment, because it is one of the sharpest crises modern science has ever faced. On one side, the firewall. To keep information alive, the smooth horizon has to erupt into flame, destroying Einstein's beautiful picture of gravity, in which the edge of a large black hole is a perfectly ordinary patch of space. Accept the firewall, and you accept that our best theory of space and time fails at the very place it should work fine. On the other side, information loss. To keep the horizon smooth and Einstein happy, the escaping particle must stay bonded to its inside partner, which means it cannot carry information out. Accept that, and you accept Hawking's original nightmare, a universe that forgets, a quantum mechanics that breaks, a clockwork of reality with a permanent crack in it. Both roads demand you tear down one of the two great pillars of physics: gravity on one side, quantum mechanics on the other. For a century, these two theories have been the crowning achievements of science, each tested to fantastic precision, each seemingly flawless in its own domain. The black hole is the one place they are forced to shake hands, and at that handshake, they seem to break each other. This is why the firewall paper caused such an uproar. It was not a small technical dispute. It was a stark demonstration that our deepest ideas about reality could not all be right at once, at least not in the simple forms we held them. Somewhere in the chain of trusted reasoning, a hidden assumption had to be wrong. But which one? Physicists tried everything. Some bit the bullet and accepted firewalls, willing to sacrifice the smooth horizon. Others insisted information must be lost. willing to sacrifice quantum mechanics. Most refused both and searched desperately for the flawed assumption hiding in the argument. The loose thread that, once pulled, would let both pillars stand. The trouble was that every step in the reasoning seemed solid. Information comes out. The horizon is smooth. Entanglement is monogamous. Each one was backed by powerful evidence. Yet together they screamed contradiction. It felt like a perfect proof that 1 + 1 = 3, where every line looks correct and the conclusion is plainly absurd. Picture a bridge held up by two mighty cables, gravity and quantum mechanics. The firewall argument was a demonstration that, at the black hole, the two cables pull against each other so hard that one of them must snap. Nobody wanted to lose either cable. The whole bridge of physics hung on both. The escape, when it finally came, did not snap either cable. It did something far more subtle and far stranger. It revealed that one of the trusted assumptions in the chain, the one about where information actually lives, was quietly wrong. The information inside the black hole was not sitting where everyone assumed. Its true home was somewhere no one had thought to look. And the first hint of that hiding place came from an idea so wild that when two physicists proposed it, it sounded less like a theorem and more like poetry. They suggested that the invisible thread of entanglement and a tunnel through space might be exactly the same thing. Two physicists looked at the crisis and offered an answer that sounded like a riddle. Entanglement, they said, is a wormhole, and a wormhole is entanglement. The two are the same thing wearing different clothes. The physicists were Juan Maldacena and Leonard Susskind, and in 2013 they wrote it down as a short, startling slogan: wormholes equal entanglement. In their shorthand, the two ideas were set equal, one on each side, joined by a bridge of pure logic. To feel how bold this is, you need both halves. A wormhole is a tunnel through space, a shortcut that connects two far apart places directly, so that stepping into one mouth drops you out the other, across the galaxy. It is a feature of gravity, of curved space and time. Entanglement is the ghostly link between two particles, that spooky bond that ties their fates together no matter the distance. It is a feature of the quantum world. For a century, these lived in separate rooms. Gravity described bridges through space. Quantum mechanics described the invisible threads between particles. Nobody thought they had anything to do with each other. Maldacena and Susskind proposed that they are secretly identical. Every entangled pair of particles is joined by a tiny, unimaginably thin wormhole, and every wormhole is really just a lot of entanglement, sewn together into the shape of a tunnel. Here is why this matters so much for the black hole. Remember the escaping radiation and the black hole it came from, tied together by countless threads of entanglement. If entanglement is secretly a wormhole, then the radiation drifting far out in space is not really disconnected from the black hole at all. It is joined to the interior by hidden bridges through space, tunnels woven from the entanglement itself. That means the inside of the black hole is connected to the distant radiation directly, through wormholes, even though they seem to sit light years apart with a horizon between them. The interior and the faraway glow are stitched together beneath the surface of space, linked by tunnels no telescope could ever see. Think of two distant lakes that look completely separate on the map. You would swear no water passes between them, but hidden deep underground runs a channel connecting the two, so that they are really one body of water in disguise. Maldacena and Susskind were saying that entangled things, however far apart, are joined by exactly this kind of hidden channel through the fabric of space. This began to melt the firewall away. The escaping particle needed to be bonded to both the old radiation and the inside of the black hole. That seemed to break the monogamy rule, demanding two full bonds at once. But if entanglement is a wormhole, then perhaps the inside partner and the old radiation are not two separate things after all. Perhaps they are connected through the wormholes into a single system. and a particle can be fully entangled with one system without breaking any rule. The contradiction started to dissolve. The information inside the black hole might already be reaching out, through hidden tunnels, into the very radiation everyone was watching. It was a gorgeous, dizzying idea. But it was still a slogan, a vision, more picture than proof. To turn it into hard physics, someone had to find where, precisely, the inside information was hiding, and write down the exact rule that governs it. And the road to that rule ran through one last idea from Hawking himself, near the very end of his life. Near the end of his life, Stephen Hawking returned one final time to the paradox he had created, with a gentle new idea. Maybe a black hole is not as bald as everyone thought. Maybe it grows a faint kind of hair. Recall the old no-hair rule. A black hole was supposed to keep only 3 numbers: its mass, spin, and charge, and erase everything else. Perfectly smooth, perfectly bald, holding no record of what fell in. That baldness was a big part of why the information seemed lost. If the horizon remembers nothing, there is nothing to carry the secrets back out. In 2016, Hawking, together with Malcolm Perry and Andrew Strominger, challenged that boldness. They argued that the horizon can carry incredibly subtle marks, tiny imprints left behind by whatever falls in. They called these marks soft hair. Soft because the imprints are made by particles with almost no energy at all, so gentle they had been overlooked for decades. The idea is that when something crosses the horizon, it leaves a faint fingerprint on the surface, a whisper of extremely low-energy particles clinging to the edge. Different things falling in leave different fingerprints. So the horizon is not a perfectly blank sphere after all. It carries a delicate record, written in the softest possible ink, of the history of what it swallowed. If that record exists, then the black hole is no longer a perfect eraser. The information that seemed to vanish could be stored in this soft hair, sitting quietly on the horizon, waiting to be released back into the radiation as the black hole fades. The secrets were never destroyed. They were pressed into the surface as marks too faint for Hawking's original calculation to notice. Picture fresh snow on a wide field. A perfectly bald black hole would be like snow that heals itself instantly, erasing every footprint the moment it forms, keeping no trace of who walked across. Soft hair is the ordinary snow we know, where every footstep leaves a mark. Read the pattern of prints, and you can tell exactly who passed by and where they went. The horizon, Hawking now suggested, keeps footprints. This was a moving turn in the story. The man who first argued that black holes destroy information spent his final years searching for the place where that information might be safely kept. He had crossed all the way from claiming the universe forgets to hunting for the exact ink in which it remembers. Soft hair did not solve the paradox on its own. It was a clue, a hint that the horizon holds more memory than anyone believed, a suggestion of where the missing record might live. It reopened the surface as a storehouse of secrets, richer and more detailed than the bold old picture allowed. But a clue is not a mechanism. To truly bend the page curve, to prove from the raw equations that the entanglement peaks and falls, physicists needed a precise tool, a way to calculate exactly how much information a black hole is hiding at any moment and where. They needed a new kind of ruler, one that could reach behind the horizon and measure the secrets directly. And in the years after Hawking's death, they finally built it. The breakthrough tool was a new way of measuring a black hole, a strange kind of ruler that reaches through the horizon and asks a sharp question: where, exactly, is the true edge of what the outside can know? This tool grew out of holography, and it has a formal name: the quantum extremal surface. The idea sounds abstract, but the heart of it is simple. To find out how much information is hidden inside a black hole at any moment, you look for a special surface, a boundary drawn somewhere in or around the black hole that minimizes a particular quantity, combining the size of the surface with the entanglement of everything inside it. Here is the plain version. Physicists already knew Bekenstein's rule, that the information a black hole hides is tied to the area of a surface. The new tool refined that rule with a twist. Do not just use the horizon automatically. Instead, search for the best surface, the one that gives the smallest, most honest count of the hidden information once you fold in the quantum entanglement as well. Nature, it turns out, always picks that best surface. Why does this matter? Because for most of a black hole's life, the best surface sits right at the horizon, exactly where everyone expected. The information count rises as the black hole radiates, matching Hawking's climbing line perfectly. Early on, the new ruler and the old calculation agree completely, but the tool carries a hidden power. It is always searching for the best surface. And sometimes, later in the black hole's life, a different surface suddenly becomes the winner. A new boundary appears, deep inside, that gives a smaller information count than the horizon does. And when that new surface takes over, everything changes. The information count stops rising and starts to fall, because now it is measured by this deep interior surface instead of the outer horizon. That switch is the secret behind the page curve. Before the switch, the horizon rules and the line climbs. After the switch, the deep surface rules and the line descends. The turning point, the summit of the mountain, is the exact moment nature swaps from one surface to the other. The page time is that swap. Think of it like two shipping companies bidding to carry a package, and you always go with whoever is cheaper. At first, one company is cheaper, and its price rises steadily. Then, past a certain point, a second company undercuts it, and suddenly your cost follows the second company's falling price instead. Your total cost traces a mountain, up with the first bidder, down with the second. The quantum extremal surface works the same way, always taking the lower count, and the handoff between surfaces bends the curve. This was the tool physicists had been missing for 40 years. A precise, calculable rule that produced the falling half of the page curve automatically, without anyone forcing it by hand. Feed in the black hole, search for the best surface, and the math itself turns the line around at the right moment. The promise of quantum mechanics fell out of the equations on its own, but the tool raised a haunting question of its own. When that new surface takes over deep inside the black hole, it carves out a region of the interior and declares that this region no longer belongs to the black hole at all. It belongs, somehow, to the radiation far outside. Those hidden interior regions would earn a name that captures how strange they are: islands. The math delivered a shock. Deep inside the black hole, after the halfway point, there are secret regions that no longer belong to the black hole at all. They belong to the radiation drifting far away in space. Physicists call these regions islands. Sit with how bizarre this is. An island is a chunk of the black hole's interior, sitting well behind the horizon, in a place nothing should ever be able to escape from. And yet, the equations insist that this deep interior chunk is actually part of the distant radiation. The information in the island is not stored in the black hole. It is stored, somehow, out in the glow that has already escaped, light years away. The two are the same information in two places. Reach into the faraway radiation, and you are also, at the very same time, reaching into this hidden island buried inside the black hole. The island is a piece of the inside that secretly lives in the outside. This is the payoff of everything that came before. Remember the wild slogan that entanglement is a wormhole. The island is that slogan made precise. The deep interior region is connected to the distant radiation through the hidden bridges of entanglement, so completely that it counts as part of the radiation. The wormhole picture and the island picture are two descriptions of the same startling fact. The inside of the black hole reaches out through tunnels woven from entanglement and merges with the glow far away. And this is exactly what dissolves the firewall. Recall the impossible demand. The escaping particle had to be entangled with both the old radiation and its partner inside the horizon. which seem to break the monogamy rule. But islands reveal that the inside partner and the old radiation are not two separate things. The inside partner lives in the island, and the island is part of the old radiation. They are one system, not two. So the escaping particle is fully entangled with just one thing after all. Monogamy is satisfied. No bond has to break. No wall of fire needs to form. The horizon stays smooth, and the information still comes out. The contradiction that nearly toppled physics simply melts. The mistake all along was assuming the inside of the black hole and the outside radiation were separate. Islands show they are secretly stitched into one. Picture a spy who seems to be locked deep inside a sealed fortress, cut off from the world. Then you discover a hidden tunnel running from the spy's cell all the way to a safe house in a distant city. In every way that matters, the spy is already in that faraway safe house. The cell and the safe house are one connected space. The island is that cell, joined by a secret tunnel to the radiation far outside, so that what looks trapped is really already free. This was the resolution the field had chased for decades. Information is never lost, because the deep interior, where the secrets fall, is quietly part of the radiation that carries them away. The page curve bends because these islands switch on at the halfway mark and hand the interior over to the outside. But how did physicists prove islands are real and not just a hopeful guess? The proof came from a technique so strange, it feels like science fiction. They imagined making many copies of the same black hole at once and discovered ghostly bridges connecting the copies. To prove the islands were real, physicists reached for a trick that sounds like pure fantasy. They imagined taking a black hole and making several identical copies of it, all at once, side by side. And in the mathematics, ghostly bridges appeared, connecting one copy to another. This trick has a long history in physics. When a quantity is too hard to calculate directly, you sometimes make several copies of the system, work out how the copies relate, and use that to pin down the answer for a single one. The copies are a mathematical scaffold, a way to get a grip on something slippery. Here, the copies were whole black holes, and the quantity being chased was the entanglement of the radiation, the very thing that draws the page curve. When physicists set up several copies of an evaporating black hole and turned the crank, they expected the copies to stay separate, each minding its own business. Instead, the equations produced something astonishing. New solutions appeared in which the interiors of the different copies were joined together by wormholes, tunnels through space, linking one copy of the black hole to another. Physicists named them replica wormholes, after the copies, or replicas, that they bridge. These replica wormholes were not put in by hand. Nobody chose to add them. They emerged on their own, demanded by the mathematics of gravity itself when you honestly account for every possibility. Gravity, it turns out, allows space to connect the copies through hidden bridges, and those bridges carry real weight in the calculation. And here is what they did. In the early life of the black hole, the plain solution wins, the one where the copies stay separate, and the entanglement climbs, matching Hawking. But later, after the halfway point, the replica wormhole solution takes over. The bridged copies give a smaller answer, and nature always takes the smaller answer. Once the wormholes dominate, the entanglement turns around and falls. The replica wormholes are what bend the page curve down. So, the ghostly bridges between the copies were the deep reason the islands exist, and the deep reason information escapes. The two pictures locked together perfectly, replica wormholes in the copies, islands in the interior, both saying the same thing. The inside of the black hole is connected to the outside radiation, and that connection carries the secrets out. Think of it like solving a maze by printing many copies of it and laying them in a stack. Working with one copy alone, you are stuck, but then you notice you can drill straight down through the stack, tunneling from one layer to the next, and those tunnels reveal a path you could never see in a single sheet. Replica wormholes were those tunnels through the stack of copies, and they exposed the hidden route the information takes to freedom. The most beautiful part was where these bridges came from. They fell out of the same theory of gravity that Einstein wrote down a century ago, applied carefully to the quantum world. Nobody had to invent new physics or break either pillar, gravity and quantum mechanics. The two cables everyone feared would snap turned out to cooperate all along, once you let space connect in ways no one had dared to include. This was the machinery the field had lacked since 1976, a concrete calculation built from trusted physics that made the entanglement rise, peak, and fall on its own. The pieces were finally in place for the moment everything came together. In 2019, after more than 40 years of struggle, a handful of physicists finally did it. They calculated the page curve from the raw physics of a black hole and watched the line bend the right way. The names deserve to be spoken. Working in overlapping groups, Jeff Pennington, and separately Ahmed Almheri with Netta Engelhardt, Donald Marolf, and Henry Maxfield, and soon Juan Maldacena and others, brought together every tool the story had produced: holography, the quantum extremal surface, islands, and replica wormholes. Alone, each was a fragment. Together, they became a proof. They set up an evaporating black hole and tracked the entanglement of its radiation, step by step, using the new ruler that always searches for the best surface. And the math did exactly what Don Page had dreamed decades earlier. Early on, the entanglement climbed, matching Hawking perfectly, as the horizon surface ruled the count. Then, at the halfway point, the deep interior surface took over. The islands switched on, the replica wormholes dominated, and the line turned. It reached its peak and began to fall, sliding smoothly down to zero at the black hole's death. The mountain appeared, the full page curve, both halves, rising and falling, produced not by hope or hand-waving, but by honest calculation from gravity and quantum mechanics working together. For the first time, physicists could point to the equations and say, "Here, this is why information escapes. This is the mechanism." The line bends because the interior secretly belongs to the radiation, and the math proves it must. This was the answer to Hawking's 40-year-old challenge. He had shown, with a solid calculation, that his radiation looked featureless, and the information seemed lost. Now, an equally solid calculation showed that when you account for the islands, the entanglement follows the curve of a universe that remembers. Hawking's original math was not wrong, it was incomplete. It missed the deep contribution of these hidden interior regions, the islands stitched to the faraway glow. Think of it like a detective who spent decades certain a locked room had no exit because every door and window was sealed. The new work found the trapdoor under the rug, the hidden passage that was there all along. Once you include it, the mystery of how the prisoner escaped dissolves completely. The room was never truly sealed. The information was never truly trapped. The relief and wonder in the physics community were enormous. A problem that had defeated the greatest minds for 2 generations had finally cracked open, and it cracked using the very theories everyone feared it would destroy. Gravity survived. Quantum mechanics survived. The promise held. Information is preserved, even through the birth and death of a black hole, and the resolution carried a gift beyond the paradox itself. It showed that space and entanglement are woven together at the deepest level, that the interior of a black hole can be part of distant radiation, that geometry itself grows out of quantum connections. The black hole, in trying to break physics, had instead revealed how physics truly fits together. But we should be honest about what was proved and what was not. This triumph came in carefully chosen, simplified worlds, model universes built to make the math possible. The victory is real, yet the story is not fully finished, because the black holes in these calculations are not quite the black holes hanging in our night sky. So here is the answer. After 40 years of struggle, the information was never destroyed. It was scrambled beyond all recognition, hidden in the deepest possible code, and then slowly handed back to the universe, particle by particle, as the black hole faded away. Let us gather the whole journey into one clear picture. When something falls into a black hole, its information does not vanish. It gets encoded onto the black hole, mixed and scrambled by the fastest scrambler in the universe until it is unreadable by any simple measurement. For a while, that scrambled record stays hidden, and the escaping radiation looks like meaningless static, exactly as Hawking found. Then comes the halfway point, the page time. From that moment on, the deep interior of the black hole, through the hidden islands, begins to belong to the radiation that has already escaped. The connection runs through bridges woven from entanglement, the same bridges that appeared as replica wormholes in the math, and through those bridges, the scrambled information starts flowing out into the glow. Each new particle that leaves carries another piece of the recovered secret until the final flash releases the last of it. When the black hole is gone, nothing is missing. Every secret that fell in is now written into the radiation drifting through space, scrambled and spread across countless particles, but fully present. In principle, a being patient and clever enough to catch every particle and untangle the code could reconstruct everything the black hole ever swallowed. The book was never burned. It was translated into an impossibly complex language and mailed out one word at a time. This is why Hawking conceded his bet. This is why the promise of the universe still stands. Information cannot be destroyed, not even by the most extreme object in creation. The black hole, which looked like the perfect eraser, turned out to be the universe's most elaborate filing system, keeping perfect records in a form too scrambled for us to easily read. Think of the whole thing as a message written on a pane of glass, then that glass shattered into a fine powder and scattered on the wind. To anyone watching, the message is destroyed, gone forever. But not a single atom of that glass was lost. Every speck still carries its part of the writing. With enough care and enough time to gather every grain and fit them back together, the message reappears. A black hole treats information exactly this way. It shatters and scatters, but it never truly destroys. There is a deeper lesson tucked inside this resolution, and it may be the most important part of all. The reason information escapes is that the inside of the black hole and the outside radiation are secretly connected, stitched together by entanglement into a single system, which means space itself, the apparent gulf between the trapped interior and the distant glow, is not as solid as it looks. Entanglement reaches across it, binding far apart places into one. The black hole taught physicists that geometry and entanglement are two sides of the same coin, that the very fabric of space may be sewn together from quantum threads. In trying to break the laws of physics, the black hole handed us a clue about where space and time themselves come from. Yet for all this triumph, an honest scientist has to admit the work is not done. The proof lives in simplified worlds, and the black holes overhead are wilder than any equation has fully tamed. For all the celebration, the honest truth is that the paradox is solved in miniature, in tidy model universes, and not yet fully in the real one that hangs above our heads. The calculations that bent the page curve were done in carefully chosen settings. Many use a special kind of space, a universe shaped in a way that makes the holographic dictionary exact and the math tractable. Others work in simplified worlds with fewer dimensions, toy versions of gravity built precisely so the equations can be solved. In these controlled arenas, the victory is complete and rigorous. The islands appear, the replica wormholes form, the information comes out, but the black holes in our sky do not live in those tidy arenas. They live in ordinary space, the sprawling, expanding universe we actually inhabit, which does not have the neat boundary the exact holographic dictionary relies on. Nobody has yet written down that dictionary for our real universe. So while physicists are confident the same story holds, they cannot yet prove it with the same airtight rigor for a genuine star-eating black hole out in the cosmos. There are deeper puzzles still open. The islands and replica wormholes tell you the information comes out, and they get the entanglement curve exactly right. But they do not yet spell out, in full detail, how to actually read a specific secret out of the radiation. If you dropped a particular book into a black hole and caught every particle it emitted, the current understanding assures you the book is recoverable. It does not yet hand you the decoder to reconstruct the words. The mechanism is understood in outline, not yet in every line, and the strangest questions of all remain wide open. What does it actually feel like to fall inside a black hole once you take all of this seriously? What really sits at the center, where gravity crushes everything to a point and our equations break down completely? How does the smooth space of Einstein truly emerge from the quantum threads of entanglement in full detail for a real black hole? These are live mysteries, chased right now in research papers appearing every month. So the picture is a genuine breakthrough resting beside a genuine frontier. Physicists are rightly thrilled. They found the mechanism, proved that information survives, and dissolved the firewall, all using the trusted pillars of gravity and quantum mechanics. That is a monumental achievement, one of the great triumphs of theoretical physics in our lifetime. And at the same time, they know the full story, for the actual black hole spinning in the depths of space is still being written. Think of it like the first successful flight of a small aircraft, built and flown in a calm, controlled field. It proves that flight is possible, that the principles are sound, that the dream is real. It does not yet mean you can fly through any storm, across any ocean, in any weather. The proof of concept is done. The full mastery lies ahead. This is how science actually moves. A paradox that seemed to threaten the foundations of physics turned into a doorway. Walking through it, physicists did not just save the old rules. They glimpsed something far grander waiting on the other side, because the deepest message of this whole saga is not really about black holes at all. It is about the nature of space and time and reality itself. The black hole set out to break the laws of physics, and in failing, it revealed the most astonishing secret of all. Space and time themselves may be woven from entanglement. Follow the thread back through the whole story. The information escapes because the inside of the black hole is connected to the outside radiation. That connection is entanglement, the ghostly quantum bond between distant things. And that same entanglement, in the wormhole picture, is a bridge through space, which means the connections we call space, the very sense that two places are near or far, may be built out of quantum entanglement at the deepest level. Turn that over slowly, because it is one of the most profound ideas in modern physics. We tend to think of space as the stage, the empty container in which everything else happens, fixed, given, fundamental. This story suggests something far stranger. Space might not be fundamental at all. It might be something that emerges, knitted together from a vast web of quantum entanglement, the way a solid fabric emerges from countless woven threads. Where two regions are richly entangled, they are sewn close together, and space between them is smooth and connected. Where entanglement is weak, the connection frays, and space itself comes apart. Cut the entanglement entirely, and the two regions drift into separate pieces, no longer part of the same continuous space at all. Geometry, in this vision, is entanglement made visible. The shape of the universe is the pattern of its quantum bonds. The black hole was the perfect laboratory for discovering this, because it pushes gravity and quantum mechanics together harder than anywhere else. In wrestling with the paradox, physicists were forced to see that the interior and the exterior, which seemed hopelessly separated by a horizon, were secretly joined by entanglement into one. And once you see space itself as entanglement, that joining stops being a paradox and becomes the whole point. Picture a great tapestry seen from across a room. It looks like a single, smooth image, a continuous scene of hills and sky. Step closer, and you find it is nothing but threads, thousands of them, crossing and knotting together. The smoothness was an illusion woven from individual strands. This saga hints that space is exactly such a tapestry, and the threads are entanglement, the quantum bonds tying every piece of the universe to every other. If this is right, and the evidence keeps pointing that way. Then the search that began with a simple worry about a cup of coffee falling into a black hole has led somewhere no one imagined. It has led to the suggestion that reality, at its foundation, is a web of quantum connections, and that space and time are the pattern those connections make. The universe kept its promise. Information is never destroyed, not even by a black hole, not even across the birth and death of the most extreme object that exists. And in keeping that promise, the cosmos revealed a deeper truth about itself, that the solid world around us, the distances between the stars, the very ground beneath our feet, may all be woven from the ghostly threads of entanglement. The black hole tried to make the universe forget. Instead, it taught us how the universe remembers, and hinted that everything we call reality is stitched together from quantum threads finer than anything we can see. We began with a star falling into darkness. We end with the fabric of existence itself.